the confidence interval tried to give you a window, a little estimated window on where this symbol lived. And it did it using this information, plus some degree of confidence, right? And that degree of confidence that you had made the estimate wider or narrower. If you wanted to be more confident that you were right, made the interval wider. You could be so confident that it just made the interval as wide as could be, and well, of course it's going to be. Of course the average shoe size is between 3 and 25, right? I'm not wrong, but that's a little too confident. The confidence level is too high. So a confidence interval can be useless if the confidence level is too high like that, and it is. And let's recap. We had two types of confidence interval. One of them was unfortunately more difficult because it just had more symbols that were stranger to us. We had about a proportion, so it was p hat plus or minus the z sub alpha over 2, which was related to our degree of confidence, times a standard error, which turned out to be, and it's only an estimate of the standard error because we don't have the actual true proportion p, so we had to use p hat. And this was p hat times 1 minus p hat over n. It was the point estimate plus or minus the error. And this was a standard deviation, and that standard deviation got scaled by this number. Right? And you could think of this as if, well, that number would just be the number 1 if all we needed was 68% confidence. Right? Because the empirical rule says 68% of the area is between -1 and 1. Then if I just have a 68% level of confidence, this number would be 1, and it would just be the point estimate plus or minus the standard deviation. So this was one of the type, and the other type was about a mean. It was trying to estimate the population mean. Let me actually say, so I'm going to say that P is in this interval. That was one of the types. And then the other type was that mu, the population mean, is inside of x bar plus or minus t sub alpha over 2 times s over root n. And in either case, it was a standard error that got scaled by this quantity. And down here, we're having to use this t curve because this t curve is essentially, it looks like the normal curve. It looks more and more like the normal curve the bigger that n gets. And we're having to use it because of us doing estimates, right? We don't want to mistakenly say, oh, well, we're 95% confident that mu isn't here, when really that's not 95% confidence because maybe our n was so small. So to compensate for that, they have this other distribution that shrinks and changes sizes depending on n. And like last week, where the first one that we did was the ones that were about a mu. Even though the homework has you do these, the homework has these first and then these, but you would agree, I think these are more challenging. So we did these first. And so I want to study this idea some more. So we're going to study this idea some more, but first, I was thinking on the drive over, there is a detail that I want to introduce now, before you even know what confidence or what hypothesis testing is. I want to talk about this detail now, so that way maybe, hopefully, it sticks in your head. Because by the time I get to it, in the story of what is hypothesis testing, this will be the most important part of it. So the output of a hypothesis test is a probability. The output is a probability. And it is essentially the probability of being wrong about something. And I ask you all, if you're talking to someone about whatever topic, do you like being wrong? Usually not, right? Usually not. If you are talking to the judge and explaining how you didn't run that red light and you don't need to pay this fine, you would not like to be wrong. You would not like for them to bring out a videotape that shows you running the red light. So, if I don't like being wrong, especially when I'm like in an argument, like imagine, it's not something like, oh, I have a terminal disease. Well, that's like a contrived scenario. I would love to be wrong about that. I'm talking about whenever someone makes a claim, they make a claim. Like maybe they say, I'm famous or whatever. This person says I'm famous, that they are famous. And I'm thinking, you're not that famous. I'm going to go ahead and contradict your claim, right? We're in an argument now, me and this person. So I want to be right. I don't want to be wrong in that case. And if I don't want to be wrong, what kind of probability would we expect? What kind of probability would go with the idea of me not wanting to be wrong about something? Let's start in the middle. We'll start at 50%. Pick a direction. You're going to go up or you're going to go down? Down. Okay, 40%. There's a 40% chance of you being wrong. Is that good? It's not great. It's not great. If there was a 40% chance that you were going to crash your car on the way home, would you drive home? No. What kind of probability would be acceptable to go ahead and drive home?
I would be
less than 10. Less than 10%? Okay. So less than 10% chance that you would crash your car on the way home, you would take the drive. That's getting close, right? So the probability must be low. However, you would still, on average, every 10 trips, crash your car. So maybe you want it even lower. 1%. 1% would be 1 in 100 trips, right? It's much less risky than the 10%, but it's where we need to be. It's a very small number. So we are going to be looking for, we want small probabilities about being wrong. Whatever this thing is that we're going to be right or wrong about. Does anybody have like a real ornery uncle or something, family member that just always is contradicting everything that someone says? Like they'll be watching the news. That's you?
No, so that's my mother-in-law.
That's your mother-in-law?
But then I decided to be quiet.
She's not here. Yeah, so, I mean, your mother-in-law will be listening to somebody talk about, you know, whatever, the weather. And she'll be like, no, it's not like that outside. It's not like that here. Just contradicting everything that someone has to say, right? I don't know, maybe they're having a bad few years or something. They got to contradict everything that somebody says. That's going to be you in this test. You're going to assume the role of, you're going to imagine yourself in the role of everything that passes across your desk. Here you are, you're at your desk, and your job is to listen to all these claims. You're listening to people's claims. I claim this, I claim that. I claim I'm famous. And they submit their paperwork, and you have like, I'm looking around your desk, and you have one tool at your desk. It's this one rubber stamp that all it says is denied or wrong, or, that's it. You don't have one that says, accepted. The only thing that you have at your desk is the rubber stamp that's like rejected. Boom. And that's what you would do on every single document, every single claim. That's the thing that you're going to be doing. And the test is trying to measure the probability that you were wrong to do that. Okay? You don't like to be wrong, so you want a low probability that happens. In other words, when we use our rejection tool, our rejection stamp, we don't want to be wrong about having done so. So we'll feel safe to do it if there's a small probability. If the probability is too big, we just won't do anything. We'll just give it to somebody else. Or just ignore it. Small probability. The output of the hypothesis test is a probability. That probability is called a p-value. P for probability. Okay? That is the ultimate outcome of the hypothesis test, is to get this p-value. Now, the way this is going to work is we will have an initial hypothesis. Someone makes an initial hypothesis. H sub 0. It's a 0 because to mathematicians, 0 is the first integer. This is also sometimes called the null hypothesis. And it is just a name of an equation. Right? There's an equation that goes with it, and H sub 0, that's its name. Then you have H sub 1. Of course, 1 is right after 0, so H sub 1, that's the alternate hypothesis. And the thing that people are submitting to you that's coming across your desk with the rubber stamp is the initial hypothesis, right? So the initial hypothesis says that so-and-so is famous. I do my hypothesis test. Out at the end comes a p-value. That p-value is a probability. If that probability is low enough, then since that probability is the probability about me being wrong, to go ahead and reject. If it's low enough, I'm going to reject. I'm going to reject their claim that they are famous, right? Because I'll feel safe in doing so. The probability of me being wrong is low. Now, talking about whether or not someone's famous is a lot less risky. There's a lot less at stake than crashing your car on the way home, right? So the amount of probability that we will tolerate can change depending on what's at stake, right? If we're testing a very risky new drug, but it could, save so many people. However, if the wrong person takes it, they die. Well, there's a lot at stake there. We're going to have a very stringent restriction on the p-value that we would take. That p-value had better be low. I don't want to be wrong. But if I'm trying to estimate, how long it takes you to get to work in the morning, it's like, who cares if you're a little bit off? The p-value, you probably take a lot more risk. Right? It's about risk. So, 1% chance of me crashing my car on the way home. Depends how bad I want to get home. If it's a 100% chance, I'll probably do it every time because that's like 10,000 trips. Right? So the smaller that p-value gets, the more and more willing you are to stamp rejection on their claim, which is H0. Okay. So let's figure out how this is going to. How could we begin to even test such a claim? Well, H0 and H1 are names of equations, and H0 is the name of an equation always without fail having to do with it's some statement about equality. This is equal to that. This population parameter is equal to whatever. So let's see. I'll do I'm trying to think of one that's not in the homework, so I guess I'll do wages. Let's do average wage for a teenaged laborer. Average wage for a teenaged laborer. Anybody want to make a claim what that average might be?
Average.
Make the claim for me. It's okay.
All I have is a number. I don't know how
Yeah.
to phrase it.
That on the average, a teenage laborer makes blank per hour or whatever. Say what number?
On the average, a teenager will make, say, $10 an hour.
Okay. What's minimum wage, just so I know?
$7.25.
Okay.
I thought it was. It's still $7. Depends on where you work too. You get paid pretty nice at Chick-fil-A.
Yeah.
That's true. true, or in and out.
Yeah, some of those places would be paying good. So this is our claim. The average teenage laborer makes, on the average, $10 an hour. And we would like to check that claim. So our alternate hypothesis could be as simple as, well, we just think it's different from $10 an hour. That's one possibility. You could have also said, well, we think it's less than 10, or you could have said, we think it's greater than 10, right? Because like you said, some of those places be paying pretty good. H0 and H1 are names of equations. H0 is always corresponding to the one that's about equality. Here we're talking about a population mean, so we would be referring to the population of all the teenage laborers. If we were doing hypothesis testing about a proportion, this would be P. Okay, so this is the setup. This is the first part of hypothesis testing, stating the initial and alternative hypothesis. And we don't know, so I'm going to take the opposite. I'm going to challenge your claim, but I don't know if it's higher or lower. I'm just going to say it's different from. Okay. Then, when I get my p-value in the end, if that p-value is sufficiently low, then I'll get out my rubber stamp and I'll stamp rejected on this claim. Okay. If the probability of me being wrong is sufficiently low, I will reject your claim. If that probability is not low enough, well then I won't do anything. I'll just be like, don't know. I'll be like, I don't know. Maybe they're right, maybe they're wrong, who knows? Okay? That would be what's called failing to reject. Failing to reject. Because remember, we just have the one tool. We don't have like an accept stamp. Right? Only have the rejected stamp. So I'm either going to use it or I'm going to not use it. That's the two options. Okay?
Which statement, I just created the problem, but which statement is our true statement?
No one knows.
No one knows.
You made this claim. We have a claim. We don't know what's true. But this is the claim. The average, this H0 is the claim that the average teenage laborer makes $10 an hour. And we can test the likelihood that that claim is true. How are we going to do that? Well, from last week, we knew that mu, we could use a confidence interval to discuss where mu would live. Right? And we would know with some degree of confidence whether mu was really in between these two numbers. And that degree of confidence came from the error. Okay? So let's suppose that we were looking at, I don't know, 95% confidence. We'll just suppose that, that this statement I have down here is corresponding to 95% confidence. And I gave you, I told you only briefly last week, so you probably don't remember what the name of the other 5% was. The 95% was that area in the middle, and then the area in the tails, which is the other 5%, had a different name. Huh? Yeah, because we have our normal curve, you have 95%, or in this case it's the t curve. You have 95% of the area in the middle, so that means the sum of the area in the two tails was 5%. The region in the middle was called the confidence level, and the region in the tails was called the significance level. So that 5% is the significance level. And what was the symbol we used for that? So alpha, the significance level, 0.05. So we have this 95% confidence interval down here. Corresponding to that 95%, the other 5% is alpha, that's the significance level. This significance level is our limitation on how much risk we can take in being wrong about rejecting. Right? So this is like our guiding. We don't want to have a probability that's bigger than this, because if our probability comes out bigger than this, then that would be running. Then that would be a violation of 95% confidence in this thing. Right? More on that later. Looking at this inequality down here. We're 95% confident that the mean would live somewhere in between these two limits. X bar minus t sub alpha over 2, E was t sub alpha over 2 times S over root n. That this is less than mu, which in turn is less than X bar plus that t sub alpha over 2 times S over root n. And we're going to do a little bit of algebra now. We're going to do a little bit of algebra to try and instead of just having mu in between these two numbers, where these two numbers are like just the sample mean, give or take some amount. Instead, I want a number that's related to a probability. If we try and do some algebra here to where instead of having all of this on either side, we only have this t sub alpha over 2 on either side, and all the other symbols are in the middle, then we'll have taken an equivalent statement about where we think mu lives and transformed it into a statement about if I take X bar and S and root n and someone's claim about mu, then it had better be between these two probabilities in order for us to have been 95% confident. To start us off, I'll subtract the X bar everywhere. Subtract X bar from here and from here and from here. So I'll have minus t sub alpha over 2 times S over root n is less than mu minus X bar is less than t sub alpha over 2 times S over root n. Now it turns out we'd rather have this stuff here in the middle reminding us of a z-score. And if you remember, a z-score went like observed minus the mean. So if we're going to do a test and then observe x bar, I want the x bar to come first. I want to say observe, I want to say x bar minus mu. Because remember, a z-score went x bar minus mu over sigma. Reminder, a z-score was x bar minus mu over the standard deviation. So I'm wanting to get something right here in the middle that's looking like a z-score, best I can get. And then it will be in between these probabilities. T sub alpha over 2, or not in between these probabilities, in between these numbers on the horizontal axis of our curve for which we could measure probabilities. The T sub alpha over 2 numbers would be, here's my T curve. They would be like these numbers down here. All we would be doing is saying that this computation that we're going to get here in the middle had better be somewhere in here. It could be any number in here, but it's going to be one of them, right? And we would be correspondingly 95% confident that that could happen because this was a 95% confidence interval. I want to say x bar minus mu. So I can multiply everything by -1. And it will, this would become positive. This would say x bar minus mu, and then this one would be negative. And since they're inequalities, I have to flip all the inequalities. Okay. So all these inequalities would flip this direction. Here in the middle, I would get x bar minus mu, but then I would have this one down here as positive and this one as negative. And I also don't like that because I want it to go negative over here and positive over here. So I can just write the whole thing the other direction and end up saying I can leave the negative one on the left and the positive one on the right, and then this is just x bar minus mu. Will be done if we just divide by this thing, s over root n. And now we would have the statement that a negative T sub alpha over 2 should be less than x bar minus mu over s over root n. Got to have parentheses down there on this one because I'm dividing by that number, s over root n, whatever it is. Needs to be less than T sub alpha over 2. This T sub alpha over 2, it's got that alpha. It's got that alpha. That alpha is linked to our level of confidence and our significance level. So depending on what your level of confidence or significance level is, will dictate what T sub alpha over 2 is. And evidently, if somebody makes a claim about mu, and we can collect sample data, find the mean, find the standard deviation for whatever our sample size is, then we can put all of those numbers into this formula, into this fraction. And just as confident as we were that mu lived in here, we would be equally confident that this thing needed to be between those two numbers. With this, if we were 95% sure that this happened, we're 95% sure this must happen. You with me? No? What's up? All I did was add x bar, gave you a hand-wavy argument why I could switch these two, and divided by S over root n. So that way it's in between these two numbers. Instead of I want this object in between those two numbers instead of this object in between those two numbers. Just algebra. Okay. This is going to be called our test statistic. This is going to be called our test statistic.
Just that part.
Yeah. Up here, we were estimating where mu must live. But down here, we are now positioned in such a way where someone could make a claim about what mu would be, and I can take it and put it here, and then check to see if it comes out between these two numbers. Up here, we had those two numbers. We said T sub alpha over 2. We went and got it and tried to estimate where mu lived. Now somebody's going to hand us a mu. We're going to put it in here, and then depending on the level of confidence that was used up here, be able to reach a decision about how good that claim is, whether or not this thing is satisfied. If this inequality is satisfied, if when we collect the sample data, I'm going to make up some sample X bar and S and N here in a minute about teenaged hourly wages. And we will be able to compute a test statistic. And we already had alpha. It was 5% because this was a 95% confidence interval. If, when we perform this computation, it winds up being between T sub alpha over 2 and minus T sub alpha over 2, then I'll have to just be like, I don't know. She could be right. She could be wrong. Don't know. However, if when I compute this and it is outside of this interval, maybe if this number is bigger than T sub alpha over 2, or if this number is less than negative T sub alpha over 2, then I'll reject your claim. I'll reject your claim because that will end up corresponding to a small p-value. You see, T sub alpha over 2 is a point on the axis of the t-curve. Let's say it's here, and the negative one, let's say, is here. We were 95% confident in that confidence interval. There's 5% in these tables. If we get, let's say we get our test statistic, we compute our test statistic based on your mean of $10, and this right here is my test statistic, T.S for test statistic. Let's say it ended up right there. Isn't that in between minus T sub alpha over 2 and T sub alpha over 2? Yes. Look, you can see it. It's in between them. That is an analogous statement to saying that we're 95% confident that the mean is somewhere in between these other two numbers. I had just rearranged it and said, okay, this new thing I'm calling a test statistic is in between T sub alpha over 2 and minus T sub alpha over 2. But if when we did that confidence interval, even though we're 95% confident, that's not 100%. Sometimes it'll be wrong. 5% of the time, in fact. It would be wrong. That would be like getting a test, being wrong with your confidence interval would be like the test statistic being over here in the table or over there in that table. If we were in this scenario right here, the p-value would be this shaded area in the tails past the, that's the significance level. The significance level, alpha, the p-value would be this red shaded area. Do you see how it's bigger than the white shaded area? You see how the red shaded area it overlaps the white shaded area, and it is bigger. It's a bigger number. Whatever that red area is bigger than the white area. Do we agree? Let me shade it some more so we can be sure. Here's the white shaded area. That's alpha. That's 5% in this setup. 5%. 95% was the part that was in between these two numbers. If we get this test statistic right here, if we do the computation and get this test statistic, then it would also form an area in the tails. And because the test statistic is in between t sub alpha over 2 and minus t sub alpha over 2, then this symmetric area where this is the test statistic and this is just the negative of the test statistic. Here my test statistic is maybe a negative number. Take the negative of a negative number, it would be positive. Right? You can see that the red shaded area overlaps the white shaded area because that test statistic was in between the two t sub alpha over 2s. It must happen, right? If it's in between, you're going to get a bigger area in the two tails. You're a little bit lost, and it has me worried.
No, I'm just listening to
Okay.
those pieces together.
There is a lot of pieces to go down there. And I'm saying to you that we're going to call that red area the p-value. Now look at how that p-value is bigger than the significance level. This p-value is a probability of being wrong if you reject. The p-value is the probability of being wrong if you reject. So if this happened, the probability is too great to be risking rejecting, because I might be wrong. Look how much more it sticks out than the white area. That means it's too risky to reject. I'll just say, I don't know. Right? I don't know. They could be right. They could be right that the mean is is 10 or whatever. Just in the same way that 10 would have come out in between the two numbers we put as the upper and lower limit for our confidence interval. Because having the test statistic in between these two numbers was what it meant to form the 95% confidence interval and be right. If you wanted to be, if I make the confidence interval and I say I'm 95% sure that the mean would be in between these two numbers, then it is synonymous to say the test statistic would be in between T sub alpha over 2 and minus T sub alpha over 2, and that's what has happened here. So correspondingly, I wouldn't reject their claim that 10 was right because 10 was in our confidence interval. But if this test statistic goes outside of T sub alpha over 2 or minus T sub alpha over 2, then it's rejection time. That would have been one of the cases where our confidence interval did not contain the mean. Here we see the p-value is too great, and we would what's called fail to reject. And that's because that p-value was bigger than alpha, our limitation on how much risk we can take in being wrong. Yeah.
So since it's inside there, it's failed to reject, but if it's outside of there, you would reject it?
Mm-hmm.
Okay.
Mm-hmm. All right, so let's say I've done a study now. I've randomly selected 100. I've randomly selected 100 teenaged laborers. I found that their average wage for these 100 teenage laborers, it was actually $10.50. So it's a little bit more than your claim. It's like, ooh, could be wrong, right? Well, it's not enough just to have that average be different from 10. We need to know if it's statistically significantly different from 10. Because the standard deviation that I measured with all of those folks was 75 cents. And your claim was that mu was 10. So down here is the claim. Up here is the information I collected through my study. The X bar, of course, it's going to be a little bit different from 10, but I don't know if it is different enough to be able to say with any degree of certainty that this claim is incorrect. So let's get a test statistic. Our test statistic, well, we already wrote down what our initial and alternative hypothesis was. H0 is that mu is 10, and the alternate hypothesis is that mu is different from 10. Our test statistic would be X bar, let me write the formula down again, X bar minus mu over that funny looking standard deviation, S over root n. And you got to have parentheses if you're going to use a calculator to compute that. All right, so let's see. This means I'm going to put 1050 minus 10 over 0.75 divided by the square root of 100. The test statistic I get is 6.67. wonder if I can figure out what's going to happen without quite yet getting my p-value. Can you remember just a rough estimate for a 95% confidence interval with an n of 100? Now, this is pretty close. This is big. 100 is big. So that t-curve is going to be real close to the normal curve. And what were the two scores that would have put 95% of the area in the middle? What is it on the normal curve? 95% of the area in between. If I got -2 and 2. If I got 95% in the middle, I've got 5% in the tails, that's in between the scores -2 and 2. And 100 is pretty big. The t-curve is going to be pretty close to the normal curve. So my t sub alpha over 2 and minus t sub alpha over 2 ought to be pretty close to -2 and 2. And I just got a test statistic that was 6.67. Way out here, right? Then I wouldn't have the scenario where the red area overlapped the white area and dominated. The red area would be tiny in comparison because it went way out here to 6.67 and then started to cover it. The white area was bigger than the red area. So, since that p-value that we're about to get, we haven't even got it yet, but we're about to get the p-value corresponding to our test statistic being way out here in the tail. That p-value will be small because 6.67 is way out here compared to 2. And that small p-value will correspond to a small probability that we'll be wrong, and we will reject the claim that they make $10. Because we would have found instead that, well, strictly speaking, what we would have found is just that they make something different from $10, but in all likelihood it would be that they make more than $10. We would have to do a different hypothesis test to talk about if it's more. Here we just did, is it different from 10? How would I get this p-value? Well, this test statistic here is a t-score. I'm going to use my t calculator, and I'm just going to find the area in the tails, past this test statistic. That's what your p-value is it's the area in the tails past the test statistic. So let me get my t calculator. There's my t calculator. Degrees of freedom would be 99 because that's 1 less than 100. And if I put this as standard, I can only look at one side at a time, which is fine. That just means I'll take whatever that area is and double it to get the other side. And I want to know the area that's past, 6.67. And you get this number. This is a 0, a decimal point, 10 zeros, and then a 73895. So it is 0.00000000000 73895. That's this number. It's incredibly small. If that was your bank balance, you'd be broke. You'd have nothing. You wouldn't even have, a trillionth of a penny. So it's tiny. It's tiny. And that's just this one tail over here. This is not the p-value yet, because this is only talking about the one tail. But this thing is symmetric, so to get the other tail, I would just double this. If I take this number and double it, and round to 4 decimal places, it's 0, 0, 0. It's 0.0000. It's essentially 0. Right? I think it's more likely that aliens visit right now than, like this number is probably smaller than the probability that happens. Right? Or the probability that I win the lottery tonight and then tomorrow and every day the rest of my life is probably bigger than this number. So it's an extremely small probability. And what is the probability of? That I would be wrong if I reject the initial hypothesis.
Can I see your task to get into the T-stats? What did you select?
Stats, calculators, T.
It gives me options like, oh, I see what you're saying.
Stat, calculators,
Yeah,
T.
I chose T, I see. Thank you.
Mm-hmm. Let's take a break, digest on that for a minute, and we'll try it on a problem. Just like last week, it's slow going at first, but then it just speeds up after you've done a few of them. Yeah.
Can you show me something?
Yeah.
I want to see how you input. Let me back over. I tried several different ways, and I'm just not getting it. 6.67.
Okay. So, for my numerator, okay, that's my numerator. These parentheses gather those numbers together and make them be a single object. So now it's going to say numerator divide by denominator.
Okay.
Numerator divide by denominator. So 0.75 divided by the square root of 100.
And that explains why.
Okay.
And then you put in this T-score,
Mm-hmm.
the DF. How do you do
It's n minus 1.
It's fine. And we had 100. Yes. Okay.
And you would be wanting to look at the, since our test statistic was positive, right? We would have to look at the area past it, not to the left of it. So you would have to change your inequality to be. No, it would have been greater than.
Oh, I thought.
Yeah.
Okay, I thought you were saying not to do it. I get you. Okay, thank you.
Mm-hmm. do number 7 first. I wanted to do this one first because they just give us the numbers straight away. We can get to work. What is this about? This is about student course evaluations. And there's a claim here. See this word? There's a claim. There's a claim that the population had a mean equal to 4. That on the average, a student course evaluation would usually have a score of 4. And then all the rest of these words say, do the hypothesis test. All right. So if the mean is supposed to be, if the claim is that the mean is 4, then it can't be option D, right? Because option D does not have the initial hypothesis as a statement about equality. And in the statement of the problem, they didn't tell me to test if it was less than 4. And they didn't tell me to test if it was greater than 4. Then that means I should just test if it's different from 4. So B, in this case, is the one that we want. Is it different from 4? Now they want the test statistic. Test statistic is one of those t-values. We should compute x bar minus the mean over the standard deviation. So x bar is 3.82, mu is 4.00, S is 0.59, and N was 96, so it would be divided by the square root of 96. And this is what I want to compute. And my test statistic is coming out as minus 2.99. What's up? Okay, what kind of phone you got? Is it an Apple or?
Yeah.
Then just go to google.com and search for calculator. It brings up their calculator in their right on your browser. You don't want to use the calculator that is an app on your iPhone, right? It won't be as fun. Okay? It'll be too hard. It'll be too hard when you want to compute this number is the problem. So go to google.com, search for calculator. They give you one that can get you by. It has parentheses, it has the square root, it's got everything you need. Hmm?
Mine doesn't.
What do you mean?
Found it.
Found it? Okay. It's not the app, right?
No.
Okay, it's in your browser. In Safari. Or Chrome or whatever you use. I've got my test statistic. Let me put it in. It wants it to 2 decimal places. There's a p-value that goes with this test statistic. It's just the area in the tails past the negative version and the positive version of that test statistic. So I will have my t-curve. Over here will be minus 2.99. That's my test statistic. I have to have the positive one too. That's positive 2.99. And I'm wanting this area. That area is the p-value. Now I'm only going to be able to get one of those tails in my calculator. So I'll just double the area, and that will be 2 tails. So I'll go to Stat, Calculators, T. My n was 96, so my degrees of freedom will be 95. And I'll have it compute the area to the left of minus 2.99. I can see then that just one of those tails has this as its area. So I'll have to double it to get the 2 tails. So I can see here that my p-value should equal 2 times 0.0017. And I get 0.00356. Rounded to 4 decimal places would just be 0.0036.
I still don't know this calculator on my phone.
Okay, hold on a second. Oh, they want it rounded to 3 decimal places, so just 0.004. Here's our new number. And then under the divided by, I start a new set of parentheses 1 did they ask you to test if it was less than 4.25? Because that's the answer for if it would have been checked if it's less. Because of the less than sign.
Yeah, that was. Thank you.
Yeah, so you'll know that you have to pick the not equal symbol by what they didn't say. If they wanted to make sure that you knew to pick the not equal symbol, they would have said, check whether the mean is different from 4. They didn't say anything, but that's what it would have taken. It means the same. You all right?
Yeah.
Okay. Anything else? All right, so I've got my test statistic, I've got my p-value. That p-value, what is that?
Rejecting. How do you say it? Like a rejection, whether or not you're gonna reject the claim. Oh, being wrong.
Being wrong.
My bad.
It's the probability of being wrong if you reject. Remember, you're this ornery person that always wants to reject their claim, and you just need a measure to tell you whether or not it's safe to do that. This probability of being wrong is low, very low, so we will reject this claim.
Compared to the 5% of the significant level.
Compared to, whatever their significance
Oh,
level is.
their significance, okay.
Here in this problem, they told me use a significance level of
Yeah.
10%.
Yeah.
So they would have allowed me to reject all the way up to a p-value of 0.0999. Or not, 0.09. That had a 9% chance of being wrong. I still could have rejected. So you can see just exactly how safe you are in saying that they're wrong, right? We are, there's an extremely good chance that we're not wrong here because that probability of being wrong is so low. So, probability is low to be wrong, I shall reject. If I reject, they want you to engage in a discussion about your evidence and the evidence of what action you can take based on that evidence. Now, very obviously, if my p-value has told me it's okay to reject, then that means I have the evidence to reject, right? Let's make a note here. If I reject, then this means I have sufficient evidence to warrant that rejection. But there's an equivalent statement that you could make. There's an equivalent statement that you could make. You could say, I have sufficient evidence to warrant the rejection. But let's try and say the same thing, but in terms of the alternate hypothesis. Because this rejection is about the initial hypothesis. So if I reject the initial hypothesis, then I can say that I have sufficient evidence to warrant the rejection of that initial hypothesis. That's the obvious statement, right? It's like, why'd you do that? I have proof I could do that. But if I instead wanted to talk about what happened to the alternate hypothesis, then I would have to say that I do not have sufficient evidence to support the alternate hypothesis. Anytime I'm going to reject my evidence for that rejection is good. And likewise, if I am rejecting this initial, well, the only other option is the alternate. I must be thinking that the alternate is good, right? At least better than this one. So my sufficient evidence would instead support the alternate hypothesis. It's the same idea. If I am rejecting the initial, I must be supporting the alternate. Huh?
So it would be I don't have evidence to warrant rejection.
No, if you reject, you always have the sufficient evidence to do something. Always. And in this case, I would have sufficient evidence to support the alternate hypothesis. Or, I could just say support H1. And these two statements, they mean the same thing, right? Because if I'm rejecting the initial, I must be supporting the alternate, and in either case, I have the evidence. That evidence is your p-value, which came from your study. Correspondingly, you could imagine that if you fail to reject the initial, then that's where you don't have evidence. And the same thing would follow. You either don't have evidence to reject. If I fail to reject, I do not have evidence to reject. Okay, that's obvious. I fail to reject, I do not have evidence to support the alternate. It means the same thing. So here we're going to reject the initial, and you kind of have to read what they have said in order to know which one you need to pick. So there is blank evidence to conclude that the mean is equal to, that the mean of 4, so the mean equal to 4, that's the initial, right? So this is like them saying, initial hypothesis. There is sufficient evidence to reject the initial hypothesis. There is sufficient evidence to conclude that the initial hypothesis is not correct. There is sufficient evidence. I'm rejecting, so it's always going to be sufficient here. There is sufficient evidence to conclude that this initial hypothesis is not correct. You will get to the point where all of the other questions they asked before this are easy, and this last one is hard. And it's like that for everyone. Ready for the next one? Yes. You didn't get the p-value. Did you use your t calculator? Your t calculator is the one in Saxon.
Yeah. Well, you would happen to have a cough drop. With like gum.
Okay, so you had did you get the correct test statistic? Okay. So you had 100 people in the study? If n is 99, then your DF is one less than that. So it should be 90. It won't change it by much, but it does make a difference. 98. And then with that test statistic, a minus 1.52, then you get this number. This is not your p-value, though. Okay? Because that's just one of the tails. We need both of the tails in this problem. So you have to take that number and multiply it by 2. Well, you only need 4 digits. Right? So 2 times the first 4 digits of that. Yeah, or 132 because you're around the previous ones. Let's check and see if that's. Okay. Now that p-value is pretty big. It's 13% chance of being wrong. That's a 13% chance of being wrong. That's a little steep for us. Our limitation is 10% chance of being wrong. So here you would fail to reject. You would have to fail to reject. It's too risky for you to reject on that. And if you fail to reject, then you do not have sufficient evidence to say that it is not correct. Number 8. Speed dating statistics. So in this data set, you have the women giving ratings of how much they like the male. And it's speed dating, so this is probably a scale of like 1 to 100. That's why it's only a 6. Just kidding. What's left? Could be 10. I don't really know what the scale is, but the average is 6. Standard deviation is 1.97. Okay. The claim is that, maybe it's the speed dating company that makes this claim or someone. But the claim is that our initial hypothesis would be that that the mean is 7. That it's 7. And someone has made the claim that the mean could be less than 7. Right? So we can check that claim. Our initial hypothesis has to be that it's equal to 7. And alternate to that would be that it's less than 7. And our hypothesis test can only detect whether we should reject H0. So if I wind up rejecting H0 in favor of the alternate, then they would be right, because they made the claim that the ratings are less than 7. So even if I reject here, it's only a rejection of this initial. The context of the problem still has them being correct. even though that we have that word rejection in there. Determine the test statistic. So, my test statistic is the observed value. So, I observe a 6.54 average minus the 7, which was what our mean was in the initial hypothesis, divided by S over root n. So that's 1.97 over square root of 194. And I get a test statistic of minus 3.25. .25. Remember that this test statistic is one of those numbers on the axis of the normal looking curve. So this is measuring some number of standard deviations. And if it was more than 3 standard deviations, it was an extreme observation that was rare for that to happen. And this is going to be more than 3 standard deviations away from 7. That's gonna be a p-value that's pretty low. I mean, essentially what this is saying to us is that if 7 really was the mean, and then I did a random sample and got 6.54 and 1.97, and the size of my sample was 194. And that was what I observed to happen. And 7 really is the mean. Then that would be a rare thing to occur because, look, it's more than 3 standard deviations away from the mean. And since that would be a rare thing to occur, it probably is not the typical thing to happen. Consequently, 7 is probably not what the mean is. It's probably lower. You've got this number, minus 3.25, that's going to be way off in the tail. You're going to have a tiny area. That tiny area is going to give you a small p-value, which would allow you to make the rejection. So I go to Stat, Calculators, T. My DF is 193, and I'm talking about being less than minus 3.25. Now here in this problem, we don't double the p-value. Or we don't double that area in this problem. Reason being is because this problem was not to test the claim if it's different than some number. It was to check and see if it's less. In this problem, we're checking to see, is it less than 7? So then I'm only interested in just the left tail. Or whatever, whichever tail, one tail. So if it's a less than or a greater than in our alternate hypothesis, it's a one-tailed test. You don't double that area. If it's a two-tailed test with a not equal symbol, then you do double that area because you need both of those tails. Here we just need the one tail, so this is my p-value, 0.0007. That rounds to 0.001 for 3 decimal places. That's a small p-value. That's a low probability of being wrong if we reject. This corresponds to how having all those observations with the assumption that 7 really is the mean, having all those observations happen would be a rare event because this is more than 3 away from 0. So since it's a rare event, it's probably more likely that 7 is just really not the correct number. It's more likely for 7 to be wrong than for me to have somehow picked just the right sample to get this rare event. So since the p-value is so tiny, the probability of being wrong if I reject is low. I'm going to reject. If I reject, I have the evidence. I have sufficient evidence to do one of those two things. I have sufficient evidence to reject. That's an easy statement. The alternate statement, the equivalent statement that's more confusing is that I have sufficient evidence to support the alternate. They mean the same thing. Support the alternate, reject this one. I reject you, but so I must support this one. It's the same thing. Here they're saying to conclude that the mean is less than 7. That's the alternate. There is sufficient evidence to support the alternate. That's what this one says.
My p-value is less than 8. I would think that we would have the same answer, but tell me that I'm wrong. I'm a little confused.
No. P-value is going to be less than 1 every time because 1 is the area under the curve. You can't get bigger than 1. 8 is the mean that they're claiming. That's associated with this claim. Your p-value is huge.
Comparing it to the...
There's a 15, you have a 15.5% chance there of being wrong if you reject. That's pretty big.
Comparing to the mean.
The p-value gets compared to the significance level. The significance level is what says you can take no more than this amount of risk. Right? For me in this problem, my p-value was so low, I didn't even look at the significance level. No one has a significance level this low, right? I mean, maybe if it's like, should we execute this person that's on death row, then maybe I have a significance level this low, right? There's a lot at stake. But this is about speed dating. I mean, 1% chance is like already pretty steep, and I beat that by an order of magnitude. So I feel very confident I can go ahead and object. Working out over here. Okay. That's awesome. All right then.
2 seconds.
Yeah.
So now that I got it straight and I'm comparing my p-value to the significance level, which is 0.01, and I got a 0.015. it's greater, so I failed to reject.
You didn't get a 0.015, you got a 0.155. That's 15 and a half.
I mean, sorry.
So 15.5% is way more than 1%.
Yes,
So you'll fail to reject.
yes.
Anytime you fail to reject, you don't have sufficient evidence.
Right.
Sufficient evidence to do what? To either reject H0 or to support the alternate. What is your alternate statement here?
The alternate statement is, the mu is less than 8.
Okay, and what did you put for the, what did you put in the, oh,
It says greater.
yeah,
So
that's not the alternate.
So I can't, so I'm just stating what the alternate is here, not
In
that.
most cases, yes.
Oh.
You're either saying, I don't have evidence to support the alternate, or I don't have evidence to reject the initial. All right, number 6. Blood pressure above 120, considered to be high. We have 100 measurements in this table. Okay. And evidently the mean blood pressure from that table is this, and here is the standard deviation of those 100 observations. 5% significance level, I can take no more than 5% risk. That's the claim if it's from a population with a mean greater than 120. So my initial hypothesis would be that mu is equal to 120. And my alternate would be that mu is greater than 120. So this would be the type of test that we could use to really check if this was this sample from the typical population, or has it got too many people in it with high blood pressure? Because if I wind up rejecting H0, then that would mean I'm in favor of this one. So it would tell me that these 100 people are not from the population that got used to say that the average should be 120. These people's average would be more than 120. So these are people with high blood pressure on the average. Or there's too many people in there with high blood pressure. Okay?
Yeah, I'm just confused on where it's wrong.
Which part?
The very first part.
Okay, did you pick mu?
Yeah.
Okay,
I see what it is now.
okay. Identify the test statistic. The mean that I'm observing is 123.46, and so that is above 120. But is it significantly above 120? That's what this test will check. Just how likely is it that if the mean really is 120, that you could pick a sample like this? So my standard deviation, and I need to use every number that they gave me there. I didn't up here because it was all zeros afterwards, that's implied, but down here in this standard deviation, it's 15.79376 over the square root of my sample size. and I get a test statistic of 2.19. That's a little bit bigger than 2. Remember that plus minus 2. Plus or minus 2 is what put 95% of the area in the normal curve in the middle, with 5% in the tails. So that 5% would correspond to an alpha of 5%, a significance level of 5%. Well, my significance level here is 5%. This isn't the normal curve, it's the t curve, but my n of 100 is all aspects. So I'm looking at this 2.19 and I'm thinking this is probably a little too big to fail to reject. This is in the tail, I'm thinking, and it's going to end up with an area that's pretty small. So I can get out my T calculator. And I only need the one tail this time. Why? Because of that symbol. It is not one of these not equal to symbols. It's only when that's a not equal to do you need to do both tails. So, stat calculators T. My DF would be 99. And this is a positive number that I have for my test statistic. So in order to get an area in the tail, I have to change my inequality to be the other way. Right? You get a positive number. If I get a positive number, well, I need to look to the side to the right of that positive number to get a tail area. If I got a negative number, then I'd need to look less than that negative number to get the tail on the left. And here is my p-value, 0.015. My test statistic, my p-value, 0.015. That p-value is the probability of what? P-value is the probability of what? Being wrong. You being wrong if you reject. Because you're there in your office, you got your grumpy face on, you got your reject stamp, and you're ready to use it. All you want to know is, can I use my reject stamp? Can't wait to use that reject stamp. And you're waiting on a low enough probability to do it. That's 1%, our probability of being wrong. I like to use my reject stamp. I don't like to be wrong. So if my p-value is low enough, I'm gonna use my stamp. So here I am, I'm ready to reject. I'll reject this claim that this numbers came from a population with a mean that was equal to 120. I do have sufficient evidence to, see here they have warrant rejection of and they have support. I'll need to read which event they're talking about back here. Are they talking about the initial hypothesis or the alternate hypothesis? So it says the claim that the sample is from a population, and it says greater than 120. That was the alternate. So this means I have evidence to support the alternate. You have divided right here. Green check mark. You're still grumbling up there?
Yes, because it's a little wrong, and this is like November 120. I'm gonna do it for this one. I'm going the right way, because this says greater than. Right here. Do I have the right thinking?
Okay, so you need to round this to 2 decimals and say 1.7.
Okay, so when the answers require me to.
This is not asking you for your p-value. It's asking you for your test statistic. You're typing in your
Oh,
p-value.
I skipped it. I see what it is.
1.7.
Yeah, I'm sorry.
Now you can say.
Yeah.
All right. So we did 6, 7, and 8. Let's take a break. We'll come back. We'll do 9 and 10. 9 and 10, just like what we've been doing, except they have not given us the mean and standard deviation. We'll have to compute it from this raw data. After we do those, we will do 1 through 5, which is about a proportion. Everything will work exactly the same, except it's not S anymore. It's not X bar. It's P hat and square root of P times 1 minus P over N. All right.
I think it's different based on, like the, yeah, the
The
numbers.
P value.
Yeah, I think so. I actually don't understand it being on how to determine, whether or not it's project or,
Non-intense.
yeah. Sorry.
No problem, thank you.
Yeah, I got that part wrong, so I'm probably just gonna have to study up on it a little more later.
P-value tells us if we should reject. Here, your P-value is 7%. It's high. I mean, it's kind of low, but not low enough, because the significance level is 0.5. Okay, so that means if you went ahead and rejected, it would be too much risk of being wrong. You don't want to do that. So you can fail to reject. Now, every single time you fail to reject, you don't have evidence. And it doesn't matter what anybody else is saying anywhere else in the statement. Fail to reject goes with you don't have enough evidence. Now, to know what you say on the other part, there's two options. Now, if I fail to reject and I don't have evidence, I could say, I fail to reject, I don't have evidence to reject the initial. Well, that's like an easy statement to make. I did this because I have the evidence to do that. Or you could be talking about supporting the alternate. If you fail to reject, then you do not have the evidence to support the alternate. It also means I do not have evidence to warrant rejection of the initial. So we have to read these words to know, are they talking about initial or are they talking about alternate? Well, it says down here, mean blood pressure, great. So we're talking about the alternate. So right now, what you have, it says, fail to reject, do not have evidence to support the alternate. That's what that means. If you fail to reject, it means I'm going to keep this one. I'm not going to support that alternate.
For me, it doesn't open till the 10th. What's today? It opens tomorrow for me.
For me.
Okay. I didn't.
I need a special spot to be in. I don't know why they do it. I want to know what the special spot is so I can get in and have history in class. I didn't choose yet. I'm leaning towards Gupta because it's a morning class.
See, how do you know
I can show you on the computer once it's over. It's in here.
that? Okay.
It's on Canvas.
Lead concentrations in different kinds of medicines. These are the lead concentrations, micrograms of lead per gram of medication. All right. Do a hypothesis test. Here's our alpha, 10%. So if our p-value is less than that, then we'll feel safe in rejecting. Meanwhile, the claim is that these medicines on the average have less than 14 micrograms of lead. So our initial hypothesis is that mu is equal to 14. And the alternate is that mu is less than 14. My test statistic needs to be the average that I observe from this sample minus the mean over the standard error. So let me open this data in StatCrunch. Right, click the boxes, open in StatCrunch. There's that data, and I'll go to Stat, Summary Stats, Columns. I tell it where that data is located, and I click Compute. So it says here our mean is 11.032 minus mu, which was 14. And then it's over the standard deviation. Over the square root of n.
You go stack, some you stack
Columns.
columns.
Mhm.
Like,
Did you open the data in StatCrunch?
Those outside calculated, like I did.
You have to open the data in StatCrunch. So you go back to your statement of your problem. There's little boxes next to the data at the top.
that's-
All right. I get negative 1.45 for my test statistic. In my T calculator, that corresponds to an area of 0.09. So there's my test statistic, minus 1.45. P-value 0.090. And 9%, it's 9% is pretty high, but simultaneously it's pretty low. We just need to defer to the boss here, the significance level, to see if it's low enough. And 9% is less than 10%, so it's low enough. The probability is low enough for us to go ahead and reject. We feel safe in performing our rejection because the p-value is the probability of being wrong if we reject. Since that probability is low, I'm going to reject. Anytime I reject, you have sufficient evidence. So,
Okay, so let me explain it. So my p-value is 0.09, but then my significance level is 0.01.
okay. 0.01 or 0.10?
0.01.
Okay. So you have a 1% significance. That's the limit on the risk you can take to reject. And your p-value is 9 times as much. It's way bigger. So it's too risky for you to reject.
So what's the difference between fail to reject and an accept?
We can accept means somehow that you've proven it true. You'll never accept. That's a red herring of an answer.
Okay.
There is no circumstance where we can accept the null hypothesis. We can never prove it true.
Okay.
We can only say it's likely wrong or do nothing. If we do nothing, that's fail to reject. It's likely wrong, that's reject.
Okay.
So we reject the null hypothesis. That means I've got sufficient evidence, and it's going to be sufficient evidence to support the alternate, which is the same thing as rejecting the initial. Now here they're talking about the alternate because it says less than. So I will support that. It's a pretty small test statistic. Yeah, but we're not doing the p. It's not the p-value. It's the test statistic. So having that test statistic, when it's that close to zero, it can happen. But for it to be that close to zero, you would need this two numbers here to be very close to zero. They're very close to each other. So you divide it by the square root of 0.01. That's not how many people you have in this study. How many medicines are in this study? I don't know if there's 14. I think so. They're just grabbing a number, 14. N, lowercase n. This number down here is lowercase n. See, that's because there was 100. There was 100 blood pressures. Do you have 0.01 medicines?
No.
No. How many medicines?
What is that?
1, 2, 3. 10 medicines. This would be the square root of 2. All right. We doing okay everywhere else? P-value is super low. Okay. You feel safe in rejecting? Then why do you fail to reject? You need to put reject. Here you're going to reject because that likelihood of being wrong is really slim, right? This thing measures the probability of you being wrong if you reject. So since it's low, we reject. Now, anytime you reject, you do have the evidence, sufficient evidence. Sufficient evidence to do what? It would be to reject the initial or to support the alternate. You have to read their words to see which one they're talking about. See how it says less than?
Yeah.
That means they're talking about the alternate. So you would support that alternate. You're going to reject the initial. Okay. That means you do have evidence to support the alternate. How much of it? Oh, that's not O. I thought it said 0, 0, 0.
No.
Okay, my bad. So yes, 0, 0, 0 would have been a 0% chance. You had a 9% chance.
Oh, okay.
Okay.
So
Sorry.
fail to reject.
Just quick fix. So most of the stuff we just, this is all still new. Still 14. You still just need those numbers from summary stats.
I have a question.
Yeah. Okay, if you're done with this problem, you can try the last one. That's pretty much the same about car seats.
So, you want him to take it down, right? Cause I wasn't getting, how does he get the D?
DF is n minus 1. Okay. 10 minus 1 is 9%. Is that the correct test statistic? Minus 1.4?
Yeah,
You've got it right in here?
yeah.
Then this is your p-value, 0.092. So you put 91% instead of 0.092.
Oh,
So 9% chance of being wrong, that's a lot more than a 1% chance. 1% was the limit, so you'll fail to reject. Anytime you fail to reject, you don't have the evidence. And here you don't have the evidence to support the argument.
He's saying wrong.
It's because you put is. Fail to reject means you do not have sufficient evidence. Uh-huh.
You want us to do what number again?
Number 10. It's got to be less than there because your score is negative. If you did positive, it wouldn't be a tail. So 0.092. Okay, it's more than alpha. Alpha is 1%. We're up here at 9%, so we'll fail to reject. It's too risky for us to do it. Anytime you fail to reject, you don't have the evidence. And here they're talking about the alternate, so we can't support that alternate. Mhm. HIC, and this number 10 means head injury condition units. So it's trying to measure the safety of, the degree of safety that a car seat provides. It's measured in head injury condition units. And the Safety Commission requires that it be less than 1,000, right? Now, quite a few of these are less than 1,000. This one's not. That one might be unsafe, right? But we want to know based on this sample of car seats that we selected here, are car seats safe? Are they meeting the criteria for being less than 1,000 head injury condition units? So mu is equal to 1,000 or it's less than 1,000. I'll open my data in StatCrunch so I can use my summary stats. Okay, so the mean is 687. And it was supposed to be up at 1,000. That's kind of low. Or I mean, it's 687. That's good because it's less than 1,000. But I need to know if it's low enough. So I'll have to divide by this standard deviation, which is 257.33 over the square root of 6. Now this test can be pretty sensitive to the number of decimals that you carry. But I mean, we're talking about 687 and 1,000. You know, a couple of decimals way after the decimal point probably isn't going to affect much. So I'll just do 257.332 divided by the square root of 6. And I get a test statistic of minus 2.98. My p-value. Well, this is going to be a small df. So look at how crazy looking my curve is. Huh? Why is it 5? Because how many car seats are there? And it's 1 less than that. And my test statistic is minus 2.98. So my p-value is 0.015. I think that in every example I've worked so far, my p-value has been really low. Oh, they went to 4 decimal places. Let me back up here. 0.0154. My p-value is a 1% chance, 1.5% chance I'd be wrong if I reject. The cap on how much risk I can take is 5%, so I'm cool to reject. We shall reject that initial claim. Anytime I reject, I have sufficient evidence. Of what here? Well, evidently it's to support the alternate. So if I'm saying I support this alternate, then I'm saying that this sample comes from a population whose average head injury condition unit is less than 1,000. That means they're safe. It's a bunch of safe car seats. Or the population that it came from is safe car seats. What do the results suggest about them meeting the specified requirement? I have strong evidence that the mean is less than 1,000, even though one of them had a measurement that was greater than 1,000. That's 6 through 10. Well, how do you know the process of how these things work? You can use that process to do the ones that are about a proportion. All you need to know is the test statistic. So when it's about a proportion, the test statistic is the thing we observe, which is p hat, minus the thing that they claim is the population proportion, which is p, divided by that standard deviation, which is p times 1 minus p over n. Now be careful here, because last week when we did this, it was p hat that we used here. And that was because p hat, we were using p hat as an estimate of p. But now this week, somebody is telling us, hey, this is p, use it. So we'll use it down here in our standard deviation. So this is the test statistic for hypothesis testing about a proportion. And I think we can go to number 1. All right, suppose that in a random selection of 100 candies. So we go to a big box of candy, pick some out, pick 100 of them out, and 20% of them are blue. So I picked out 100. That means 20 of them are blue. 20% consequently are blue. But even though I did a random selection, the candy company claims that the percentage is really 29%. Right? The proportion is really 0.29. That's their claim. Let's check that claim. They don't say to check to see if it's greater than or less than, even though you might believe it's less than, but we weren't instructed to check if it's less than. The claim that was made is that the percentage is equal to 29. They did not make the claim that it is greater than 20, which is a different type of problem. They didn't look at my claim and challenge it by saying, no, it's greater than that, and that's our claim, and we can check it. Instead, they just said, here, it is equal to 29, and we'll check to see if it's different from 29. So this is going to be one of those two-tailed hypothesis tests where we'll need to double that area we get. Our test statistic should be the observed proportion minus what they claim is the true proportion over the standard deviation of the proportion. Okay, well, when I did my random sample of candy, I got 20% of them blue. They're telling me that it should be 29%. Right? I got 20% of them blue. They're saying 29%. And then this would be divided by the square root of 0.29 times 1 minus 0.29, but I do not want you to even write that. I want you to explicitly and separately first compute. What is 1 minus 0.29? Well, it's just like making change for $1. It's $1 minus 29 cents, okay? So it's going to be 71 cents.
So you're saying do the denominator separately?
Not do the denominator separately. Do this part separately.
Oh.
Okay? Don't get it's not worth it to put 1 minus 0.29. It's too muddy in the calculator. There's too much opportunity to mess up. Explicitly compute that 1 minus 0.29 is just 0.71. And then when it's calculator time, you'll be typing 0.29 times 0.71, and you'll have better luck getting the right number with less error. Divided by the square root of n. Well, n was 100. So this is our, what's up?
So we're putting, 1 minus 2.1, I get that.
Look, it's right here.
0.7.
It's 1 minus p. 1 minus p. What is p in this problem? P is 0.29. If you're buying something for 29 cents and you put out $1, they'll have to give you 71 cents. And that's where I get the 0.71. Yeah. All right. 0.2 minus 0.29. And I get a test statistic of minus 1.98.
I'm sorry.
So-
I just don't understand the points of it.
Look at the correspondence between these two. They're equal. Okay? Since they are equal, this is telling you that this is that, right? And this is that. Agreed so far?
Yes.
Here's P again, because it's right there. Now look at this and tell me what 0.71, where does it come from?
One point .71?
No. What,
Oh,
your question is, you don't know what this, where this comes from.
yes.
And I'm telling you to look back over here to see what it comes from. In the same way that the 100, well, that must be what the n is. So this 0.71 must be what this is. 1 minus p.
1 minus. Yes. Don't ask me why I took .01. Don't ask me why I did that.
Okay, I won't answer.
I'm here with you.
How would you enter it in the calculator?
How would I enter in the calculator? I would say, open parentheses, 0.20 minus 0.29, close parentheses, divide, square root. It already puts in open parentheses for you there. And then 0.29, and then times 0.71, and then divide 100, close parentheses, equals. Time to get my p value. But we don't use the t curve here. We're using the z curve, the normal curve. So I go to StatCrunch, open up my normal calculator. And I give it this z-score of minus 1.98. I get an area in the tail past the test statistic. But this area is not my p-value here because this is a two-tailed hypothesis test. Our hypothesis test here was that the alternate was not equal to 0.29, so I would have to double this number. So my p-value is 2 times 0.0239. Which comes out to be 0.048. So that means there's a 4.8% chance that I'd be wrong if I rejected the initial hypothesis.
Can you go to, the p-value again?
Yeah, I went to my normal calculator, not the t calculator this time,
Oh,
the normal calculator. And I gave it my test statistic, minus 1.98. And it told me that that little piece of area in the tail past that test statistic was this amount of area. But this is a two-tailed test. This is a two-tailed test because my alternate hypothesis was that the proportion was different from 0.29. And it's that not equal symbol that means it's two tails. I need both of them. I need both tails, right? So I had to take that 0.0239 area and double it. And I get 0.048.
That's just normal.
Huh? You don't see the normal calculator?
No, not till I see it.
Okay. .8% chance of being wrong, but they had me capped at 1%, so it's too risky for me to reject. I'll fail to reject. Anytime I fail to reject, I do not have sufficient evidence to make that rejection. Beginning or not? You are? Yeah. Did you put in too many decimal places? Because then we went to 2 decimal places. 1.21. Because the next digit is 7. Yeah. Right, normal curve. And you need the area past 1.21. Is it working or not?
Oh, I need 2 calculators, that's fine.
You good? Yes. Is that an area in the tail? That big red area, is that a tail? Or is that like the body? You don't want the body, you want the tail. You see how you have it? You say 1.96, and then this says to the left of 1.96. There's 1.96, and you have asked it, where's the area to the left? That is not a tail. This side's a tail. No. 1.96 is a z-score. It goes into the z-score spot. You can never put it in the area spot. It's not an area. Okay? That's going to give you the exact same thing. Because you're still asking for the area to the left of that mountain instead of to the right. Now that's a tail. That's a small number.
times 2.
And that gives you the probability. See, one red flag was that you were trying to tell it that you had a probability that was bigger than 1. Well, that means it's better than guaranteed. Well, that can't happen. That's not a tail. That's the body. That's a tail. Okay. That's a tail area. And you need twice that. Is it the right test?
No, it's not. I don't know what I'm doing. What you mean?
What's up? Okay.
So this is what I got for.
That would be half a year. Show me the normal calculator.
So I'm supposed to take.
Tell me what this is as a percentage. You should be able to just look at it.
0.0.
it down.
Take the decimal, move it two places to the right. Tell me what it says. It's 2.4. That's about 2%. It's more than 2.5%. That's 2.5%. That's 2.5% of the area under that curve, not 25%. Back at your book right then. You put almost 25%. You guys are going to be nurses. Just imagine if somebody needed a medication and the solution was for you to put 2% of this medication into a solution, stick it in their IV bag. But instead, you put in 25%, and they keel over because you couldn't know the difference between 2.5% and 25%. That percentage stuff, let me tell you, is probably, like, of all the math things you could learn at this school, going to be the most important one. Those details. Details. Problem 2. We have a drug that's used to treat nausea. All right, I got 230 subjects, that's N, and 50 of them got nausea. So my p hat must be 50 over 230. I'll get that number to 4 decimal places. And so I get 0.2174. That's my p hat. Tests that claim that more than 20% of users develop nausea. So this will only be a one-tailed test because of the greater than symbol. My test statistic would be the proportion that I witnessed get nausea, 0.2174. That's 21.7%. I saw 21.7% of them get nauseous. But it's like maybe the drug manufacturer is saying, no, only 20% of them should get nauseous. That's the 0.2. And then we divide it by the standard deviation, which would be 0.2 times 1 minus 0.2 over the square root of n. All right, don't have to square root, the square root's already on the outside. So it's over 230. Say what now? Yeah, that's my p hat. It's at the top of the screen. It came from 50 over 230. 50 of them got nauseous. Out of how many? 230. P hat, that's the X bar, but it's for proportions. So it's the proportion of people that I saw get nausea out of my 230 folks. I had 230, 50 of them got nauseous. 50 over 230. My test statistic is 0.67 or 66. Pretty small test statistic. That test statistic's getting close up to 0, right? And my normal curve has its middle at 0. So with this test statistic getting up close to 0 means I'm going to have kind of a big area past it, right? If I'm going to have a big area past it, that's going to correspond to a big p-value. So I'll probably end up failing to reject here, finally. Yes, that's where? Well, there's no difference.
Oh,
Because if I just put 0.2, it could have zeros forever after it. It'd be the same thing. Unless you're in chemistry class, where they'll be different over there. But to math people, it's p-value. So go to StatCrunch. Get my normal curve, stat calculator's normal. There it is. Tell it my z-score, because this test statistic, it is a z-score. It is a z-score just like in every sense of the word, because it is an observed minus a mean over a standard deviation. So here we are on the normal curve, and I'm learning that, whoa, I have 25% of the area under this curve in the tail right there. Okay? I have a positive score, so I need to be looking to the right of that score. So that way it'll be a tail. If I look to the left of that positive number, it'll end up including the top. That'll make it the body. I don't want that. And I think this was a one-tailed test. Yeah, because this was a more than. So one-tailed test, and that number I get, that's my p-value. I don't double it. You only double it when it's a two-tailed test. So my p-value is 0.255. 25.5% chance that I would be wrong if I reject. Well, that's too much risk. So I should fail to reject. Anytime I fail to reject, I do not have the sufficient evidence. Sufficient evidence of what? To warrant rejection or to support the alternate. They mean the same thing. Here we're saying support the alternate. I fail to reject, I do not have evidence to support the alternate. If I can't support the alternate, that does not prove the initial one true. It just shows that we didn't have anything to contradict that original hypothesis. So even though I saw 21.7% of my patients get nauseous, it's different than 20%, but not different enough. Not different enough for me to be so bold as to say, you know what, this 20% ain't right. It should be more than 20%. I couldn't do that. I couldn't support that alternate claim. Number 3. We have some people getting asked if they prefer to watch the news rather than to read it or listen to it. So your choices are watch it or do the other things. not watch it, yet still consume it somehow. Use those results with a 1% significance level. And what are we supposed to do? Test the claim that fewer than half prefer to watch. So if it's less than half, that's less than 50%, right? So it would be P is equal to 50%, or P is less than 50%. That's fewer than half. They've even called this test statistic a Z. It's a Z-score, normal curve. Okay. Time to get my test statistic. What did I observe happen? Well, in the survey, it was 46.7% watched the news. And I'm testing that against the notion that 50% watch the news. And then divided by that standard deviation associated with the 50%. So that's 0.5, and then 1 minus 0.5 is still 0.5 over n 1161.
I missed how you got the 15.
What does it mean to have
Oh,
half?
okay, I see it there. I see
Yeah.
it. As soon as I asked the question. Just really keep it. That's good.
And my test statistic is a minus 2.25. The corresponding p-value, I'll use my normal curve. It's a negative number for my test statistic, so I'll have to look to the left. It's a one-tailed test. They're asking me to check if it was fewer than half consumed the news by watching it. So then this number that I get is my p-value. I do not have to double it. 0.012. 0.012, that's 1%, 1.2%. And they wanted me to check with a 1% significance level. Ooh, so close. Right? They said use a 1% significance level. They said you can reject so long as you don't have more than a 1% chance of being wrong. That's what they said. So we do all this work, we get our p-value. I'll be dang, it's more than 1%, but just barely. That's a violation. This is bigger than 1. Even though it's small, it's more than our limit. So we fail to reject. I I fail to reject. Anytime I fail to reject, I do not have the sufficient evidence. And here they're talking about fewer than half of Americans. That's the alternate. And so I can't support that alternate. Doing all right? I only have 10 minutes left. Let's do this one, number 5, about the green and yellow peas. Seems like we'll probably see this problem again. 406 green peas, 137 yellow peas. Okay, so I have to add them together to get the total. So my N will be 406 plus 137. So I have a total of 543 peas. Okay. They want me to test the claim that under the same circumstances, you'll get 27% of them to be yellow. I didn't say less than 27% or more than 27%. It's just the claim is that when you do this thing again, you're going to get 27% of them to be yellow. So my initial hypothesis would be that 27% of them are yellow, or that not 27%. My test statistic will be my p hat. I have to get my p hat. Now, I had 137 that were yellow out of 543. So the thing that I witness is 137 out of 543. To 4 decimal places, that's 0.2523. Then my test statistic will be 0.2523 minus what their claim is. Their claim is that it's 0.27 over square root. Here's my 0.27. Here's the 1 minus 0.27. Well, that's 0.73. And then it's over my N, which is 543. And I get negative 0.93 for my test statistic. It's almost minus 1. my p-value. I'll use my normal curve. And I need to give it this test statistic of minus 0.93. And I wind up with this area. Now, was this a two-tailed test or a one-tailed? So I'll need to double this area. So 0.1762 times 2, I get 0.352. Now that's a 35% chance of being wrong if I reject. That's not a safe thing for me to do then, to reject. Too big a chance I'd be wrong. So I should fail to reject. Oh Lord, they want it to 4 decimal places, so let me go back. Three, 5, 2, 4. So, what am I going to do then? Well, that p-value is so big that I will have to reject, or excuse me, fail to reject. I'm failing to reject because that p-value is so much more than my significance level, alpha. Well then what, yes ma'am?
I'm getting the p-value wrong, but I'm confused what I'm doing wrong. I go to between, or no, I go standard vector normal, and then what I'm putting in is just the TS, right?
The test statistic.
Yeah.
It is a z-score, yeah.
And then I multiply that number by 2, right?
In a two-tailed test, yes.
Yeah. So I'm confused. I'm confused and asked the wrong number I'm getting.
Well, what is, so when we started, we said p-value is the probability of what? Yeah. And probabilities, if something had a probability of 1, it's guaranteed to occur. Can it have a probability of 1? So, looking back at your normal curve, is that a tail? We need to look at the tail area. And so you have more than half of the curve shaded.
Right.
And when you double it, you're going to get a number that's bigger than 1. And that's the problem. You need to look at the tail area. If your z-stat is positive, you look at the right side of it like that. Yeah. If your z-stat is negative, you would go to the left side. So here I failed to reject because that p-value I got was enormous. And that means I don't have evidence. And then I have to detect which thing I'm trying to talk about here. I don't have evidence. So if my p-value is huge, so I'll fail to reject. I cannot support the claim that, well, that shouldn't even say less than. Like it can't be C. It would seem like this could be right. But for this one to be right, it would need to say different from 27%. The only correct one here is D, because it's the one that says, I don't have evidence. I'm failing to reject. I don't have evidence to warrant the rejection. All right, number 4, I'm sure you can tend to by now. This last sentence, you can just ignore. Doesn't do anything for you, just ignore it. And work the problem as usual. All right, and I will see y'all in a week. This is week 6. So there's that midterm 2, which is over homeworks 4, 5, and 6. And then for the next 2 weeks, you have no quizzes. Rejoice.